Chapter 16, Chemistry of Benzene, Electrophilic Aromatic Substitution. As we already learned in the last chapter, benzene is an aromatic compound, and benzene undergoes aromatic substitution reaction instead of addition reaction. One of the hydrogens can be replaced by a halogen, and the reaction is called halogenation reaction. Other substitution reactions include nitration, sulfonation, hydroxylation, alkylation, and acylation. In this slide, we go over alkene electrophilic addition reactions. An alkene contains a double bond, which is electron-rich. The two electrons on the pi bond attack positive charged hydrogen, forms a carbon-hydrogen bond. At the same time, another carbon forms carbocation. Bromide attack carbocation, forms alkyl halide. The net effect is pi bond break. Hydrogen adds to one carbon, bromine adds to another carbon. Similarly, a double bond can react with chlorine molecule to form a dichloroalkane. When benzene is mixed with bromine, no reaction takes place unless we add aluminum chloride, iron bromide. And the reaction is to replace one of the hydrogen by bromine. So benzene is not simply a ring with three double bonds. For the reaction to proceed, we need a catalyst, and the reaction is a substitution reaction. Let's again compare benzene with an alkene molecule. In alkene molecule, there is a double bond which is electron-rich. Electron-rich pi bond attack chlorine. Or we can say chlorine is electrophile. Phile means love. Chlorine loves electron. So one is electron-rich, one loves electron. So they combine, let the reaction proceed. Okay. In benzene, all the pi bonds are conjugated, forms aromatic system, and that makes benzene less reactive. So in order for the reaction to proceed, we can make chlorine more reactive. Catalyst is used to combine with chlorine and forms a cation. Cation loves electron more than neutral molecule, and that's why when you add a catalyst, all right, chlorine becomes a strong electrophile, and that's why it makes a reaction proceed. Here shows how it works. Aluminum is in group 3 in periodic table. It has 3 valence electrons, forms 3 chlorine aluminum bonds. There is a p orbital that is empty with no electron, and this makes aluminum chloride a Lewis acid. A Lewis acid is a substance that can accept lone pair electron. Suppose you have a molecule with lone pair electron. This lone pair electron can go to this empty p orbital, forms a bond, and that's why aluminum chloride is a Lewis acid. So if you mix chlorine molecule with aluminum chloride, chlorine molecule has lone pair electrons. It can donate this lone pair electron to the empty p orbital of aluminum, forms chlorine aluminum bond. So the electrons in chlorine molecule shift to the right side, makes the other chlorine partially positive, eventually forms chloronium ion with a positive charge, and that makes chloronium ion stronger electrophile than neutral chlorine molecule. Let's draw the mechanism of this electrophilic substitution reaction. So we already know the first step is to activate bromine molecule by catalyst. So when these two add together, bromine becomes bromonium ion. And now even less reactive aromatic benzene, the pi bond can attack bromonium ion. So when the two electrons forms a bond between one carbon and the bromine, the other bond carbon becomes positive charge. And this step is a slow step similar to the alkene electrophilic addition reaction, where the first step also forms a carbon cation. Now, for electrophilic addition reaction, after it forms carbon cation, the other bromide ion will attack carbon cation, okay, carbon cation that forms dibromide. Now, this is not the case in benzene reactions. Instead, hydrogen that is adjacent to the carbon bond will be deprotonated, so by a base, and this base is generated in the first activation step when the iron bromide attack one bromine to form tetrabromide, iron tetrabromide with actual lone pair electron. So that's a base, can take the proton away. So this bond break, the 2 electrons goes to the carbon-carbon bond, forms a pi bond. Now, why the second step, instead of form a dibromide as electrophilic addition reaction, it actually takes another route to form a substitution reaction? The reason is by doing this, it resumes aromaticity. Okay, by forming another double bond, it becomes a aromatic compound again. An aromatic compound is a stable compound, and this is thermodynamically favorable than forming a compound with 2 double bonds. Okay, and so compare with aromatic substitution reaction with alkene electrophilic addition reaction, the first step is similar, except you need activation step by catalyst. Both forms carbon cation. The major difference is the second step. So second step in aromatic reaction, it's the elimination reaction to resume aromaticity instead of forming dibromide compound. So I want everyone to be able to draw this mechanism, all right? Practice until you can draw the mechanism. Now let's look at the mechanism of aromatic electrophilic substitution reaction. So first, the bromine molecule has to be activated by a catalyst. In this case, we use iron bromide, Lewis acid. So they combine, forms bromonium ion. Note that bromonium ion has a positive charge. So even the less reactive aromatic compound can use the pi bond to attack bromonium ion. And the 2 electrons in the pi bond forms a carbon-bromine bond. And the other carbon now becomes a positive charged carbon cation. And this step is a slow step. And this step is similar to the first step in electrophilic addition reaction of alkenes. The difference is you need an activation step for aromatic reactions. Now the second step, okay, if it's electrophilic addition reaction, the second step after forming carbon cation, bromine ion, okay, bromine ion will attack carbon cation, and that will give you addition product. Okay. However, in aromatic reaction, instead of forming this step, it actually go a different route. The hydrogen, okay, adjacent to the carbon cation is deprotonated by a base, and this base is generated in the activation step. The catalyst combined with bromine forms iron tetrabromide with a lone pair electron. So this is a base that deprotonates the hydrogen adjacent to carbon cation. So the bond between carbon and hydrogen break. 2 electrons goes to this carbon-carbon single bond, forms a pi bond. So now a double bond is generated. Now why there is a difference? Why electrophilic addition forms dibromide, but in aromatic reaction, it goes different route. The reason is by forming a pi bond, the reaction, the product becomes aromatic again. The reaction resumes aromaticity, and the aromatic compound is a stable compound, so thermodynamically it's more favorable to go this way than to go a compound with two double bonds. So compare electrophilic addition reaction with aromatic substitution reaction. The first step is similar. Both forms a carbon cation. The only difference is you need an activation step to activate bromine. Now the major difference is the second step. So second step, electrophilic addition, is the bromide attack directly to the carbon cation, but aromatic substitution reaction is the elimination reaction. The hydrogen adjacent to carbon is eliminated, forms a pi bond, so that the molecule resume aromaticity. Okay, so the mechanism has two steps. Okay, first step is addition reaction. Pi bond attack bromine, forms carbon cation. Second step, elimination reaction. Eliminate hydrogen, forms aromatic compound, the substitution compound. Okay, so I want everyone to be familiar with this mechanism, practice, so that you can draw the two-step mechanism for aromatic substitution reaction. Here shows the energy profile of the aromatic substitution reaction. So the first step is bromine is activated by a catalyst, and then the pi bond attack bromine, forms carbon cation. So that's the first step through a transition state, and the energy minimum represents this carbon cation. Note that this activation energy is quite high, and therefore this step is a slow step. Now the second step, carbon cation can be attacked by bromine, forms addition reaction. So the addition product energy is here. Another way is to eliminate this hydrogen. Two electrons goes to here, forms a aromatic substitution product. And note that the energy of aromatic substitution product is much lower than the addition product, and thermodynamically, and this is much more favorable. And in practice, and this is the only product that formed by electrophilic aromatic substitution reaction. We just showed that when benzene is mixed with chlorine and a catalyst, aluminum chloride will combine with one of the chlorine atom, and the other one forms a chloronium ion. Pi bond attack chloronium ion, followed by elimination of a hydrogen adjacent to this chlorine, and a substitution product is formed. And the net effect is a hydrogen is replaced by a chlorine atom, and this reaction is called halogenation reaction. Similarly, if you mix benzene with methyl chloride, aluminum chloride will take this chlorine away, forms a carbon cation. Pi bond attack carbon cation, followed by hydrogen elimination, forms a substitution product, and in this case is toluene. A hydrogen is replaced by a methyl group. This reaction is called Friedel-Crafts alkylation reaction. When benzene is mixed with acid chloride, aluminum chloride will take this chlorine away, forms a cation. Pi bond attack carbon cation, the carbon positive charged carbon, and followed by elimination of hydrogen, and a substitution product is formed. So the net effect is hydrogen replaced by this group, acetyl group. So acetophenone is formed. And this reaction is called Friedel-Crafts acylation reaction. Now, when benzene is mixed with nitric acid, this is the Lewis structure of nitric acid, and with sulfuric acid. So in this case, we don't use Lewis acid such as aluminum chloride. Instead, we use sulfuric acid. This sulfuric acid will take a hydroxy away. Okay, it will protonate this one, and then water leave. So you get this NO2 positive charge, and then pi bond attack here, followed by elimination. So the net effect is the hydrogen replaced by NO2. So that's the nitrobenzene. The reaction is called nitration. Benzene mixed with SO3, okay, sulfur trioxide, with sulfuric acid. Sulfuric acid will protonate this oxygen and then attack, okay, followed by elimination. And the reaction is called sulfonation reaction. So we are going to show mechanisms of these reactions in more detail. All the reactions shown above follow the same pattern of mechanism. First, electrophile is activated by a catalyst, form a stronger electrophile. The pi bond from the benzene ring attack the electrophile, forms a carbocation intermediate, followed by the second step, elimination of a hydrogen, restore aromaticity. Let's discuss the Friedel-Crafts alkylation reaction in detail. The overall reaction is a benzene ring react with the alkyl halide under Lewis acid aluminum chloride. One of the hydrogen is replaced by alkyl group, forms alkyl benzene. The activation step is similar to the chlorine molecule activation step. In this case, the lone pair electron of the chlorine donate to the p orbital of the aluminum, forms aluminum chlorine bond. Electrons shift towards the right side, carbon becomes partially positive charged, eventually forms carbocation. Now the electrophile is activated. One of the pi bonds on benzene ring attack this carbocation, forms a new carbon-carbon bond. At the same time, the other carbon on the benzene ring becomes a carbocation. The next step is the hydrogen attached to the same carbon that forms carbon-carbon bond is deprotonated by aluminum tetrachloride ion. The two electrons of the bond goes to here to form a pi bond. So a double bond is formed. The benzene ring, aromatic benzene ring, is regenerated. There are some limitations of Friedel-Crafts alkylation reactions. First, only alkyl halide can undergo Friedel-Crafts alkylation reaction. For example, benzene ring can react with methyl chloride, forms toluene. So this methyl chloride is called alkyl chloride. Methyl is a alkyl, okay, so alkyl halide. Now, if a double bond attached to chlorine, and this is called vinylic halide, and the benzene ring attached to chlorine, that's called aryl chloride, okay, aryl halide. These halides are not reactive, and they don't participate in Friedel-Crafts alkylation reaction as alkyl halide does. Okay, second, the reaction will not work with rings containing strong electron withdrawing group. Remember, when electrophile is activated, the pi bond will attack the alkyl halide because benzene ring is electron rich, so the electrons can attack the activated electrophile. However, if you have a group that can take electron away from the benzene ring, then benzene ring does not have enough electron, then the reaction cannot proceed. And this electron withdrawing group include nitro group, cyanide, and aldehyde, ketone. So all these groups, they have CO double bond. So CO double bond, Okay, so this is aldehyde. And if you have CH3, that's a ketone. So aldehyde ketone. And if this is OH, that's carboxylic acid. And if this is CH3, that's ester. So all these have CO double bond. And CO double bond strongly take electron away by the CO oxygen double bond. CN is CN triple bond that take electron away by this nitrogen. And NO2, you have also NO double bond. So all these are strong electron withdrawing group. And if you see a benzene ring with these groups, the reaction cannot proceed. Now, amine does not have NO double bond, so NH2, okay, in a benzene ring. Okay. In fact, it has lone pair electron, so this is not an electron withdrawing group. However, during the reaction, the product, one of the product is HCl. It's an acid. This acid will come back to react with the nitrogen base and prevent the reaction to proceed further. And therefore, if benzene contains NH2, even though it's not an electron withdrawing group, the reaction cannot proceed for Friedel-Crafts alkylation reaction. The third limitation is that multiple alkylations may occur. For example, benzene reacts with T-butyl chloride, so one T-butyl chloride may be added to benzene ring, which replaces one hydrogen. However, we know that alkyl group is electron donating, so it donates electron to make a benzene ring electron rich. In other words, this product is more reactive than the benzene itself. And so the pi bond then attack another activated electrophile at a second alkyl group. So the reaction is difficult to stop after a single substitution reaction. And usually you may make a mixture of products. Another problem of Friedel-Crafts alkylation reaction is carbocation rearrangement. For example, if you mix benzene with butyl chloride and catalyst aluminum chloride, you would expect that one hydrogen is replaced by the butyl group to form butyl benzene. However, only 35% is produced. 65% is another product called secondary butyl benzene. This is because the first step is the butyl chloride is activated by aluminum chloride, forms butyl cation. So the positive charge is on the first carbon, and this is the primary carbocation. We know that the primary carbocation is not stable. So before the carbocation react with the benzene ring, it actually tries to rearrange, form a more stable carbocation. And this is performed by hydride shift. The hydrogen on a neighboring carbon shift to the first carbon. So the first carbon now becomes CH3, but at the same time, the second carbon becomes a cation. And this is a secondary carbocation, and this is the first primary carbocation. Secondary carbocation is more stable. So by rearrangement, the carbocation forms a more stable carbocation, and then benzene attack elimination forms the product, and that's the product. Okay, this product is formed by carbocation rearrangement. Okay, as long as a reaction involves carbocation, the carbocation always try to rearrange to form a more stable carbocation before the next step to happen. So another example is when benzene reacts with this alkyl halide, and the activation step gives you again a carbocation primary. So this is a primary carbocation, and here in this case the neighboring carbon does not have a hydrogen, so it cannot undergo hydride shift. Okay, so what happens is it a methyl shift to the first carbon. Okay, so the first carbon now becomes second carbon, and then this carbon, second carbon, now becomes a carbocation, and this is a tertiary. So tertiary is much more stable than primary carbocation, and then after rearrangement, benzene attack here and forms this product. Practice. The Friedel-Crafts reaction of benzene with 2-chloro-3-methylbutane in the presence of aluminum chloride occurs with a carbocation rearrangement. What is the structure of the product? Okay, so we look at the activation step, and here is the structure of 2-chloro, so this is number 2-chloro-3-methylbutane, activated by aluminum chloride. So aluminum take the chlorine away, forms a carbocation, so the second carbon becomes positive charge. And this is a secondary carbocation. Is that possible to rearrange to form a more stable carbocation? Okay, it is possible because the neighboring carbon has a hydrogen that can shift to this carbon so that the third carbon becomes a positive charge. And this third carbon is a positive charge, is a tertiary carbocation. Tertiary carbocation is more stable than secondary carbocation, so rearrangement can happen. All right, and now the benzene ring will attack this one, and the product should be, that's the product. Friedel-Crafts acylation reaction is between a benzene ring and acid chloride. The reaction is replace one of the hydrogen on the ring by acetyl group to form acetophenol. Similar to Friedel-Crafts acylation reaction. The reaction will not work with rings containing strongly electron withdrawing groups. The reaction mechanism is also similar to acylation reaction. First, acid chloride is activated by aluminum chloride. Chlorine combined with aluminum chloride, bond break, forms acyl cation. The acyl cation has two resonance forms. After it is activated, benzene pi bond starts to attack positive charged carbon, forms a new carbon-carbon bond, and the other carbon on the ring becomes a carbocation. Second step, elimination reaction. The proton is deprotonated, a pi bond is formed, and restore the aromaticity. In nitration reaction, nitric acid needs to be activated first. Here is a Lewis dot structure for nitric acid, which contains a hydroxy group. Concentrated sulfuric acid can protonate this hydroxy group to form a good leaving group, water. Leaving group leave gives a positive charged nitrogen ion. Nitrogen ion is a powerful electrophile. Benzene's pi bond start to attack the positive charged nitrogen, forms carbon-nitrogen bond, and the other carbon on the ring forms a carbocation. Next step, elimination reaction. Hydrogen is deprotonated, pi bond is formed, aromaticity is restored. The net effect is a hydrogen on the benzene ring is replaced by NO2, forms a nitrobenzene. When treated with metal ion in acidic condition followed by base, nitro group can be reduced to amine, and the product is aniline. Aniline is a key part of synthesis of dyes and pharmaceutical agents. In sulfonation reaction, sulfur trioxide first needs to be activated. Here shows Lewis dot structure for sulfur trioxide. Concentrated sulfuric acid will protonate this oxygen, forms hydroxide. Benzene pi bond attack positive charged sulfur forms carbon-sulfur bond, and the other carbon forms carbocation, followed by elimination of the hydrogen. Aromaticity is restored. Product is benzene sulfonic acid. In summary, benzene undergoes electrophilic substitution reactions. When treated with a bromine molecule and a Lewis acid, one of the hydrogen on the ring is replaced by bromine, forms bromobenzene. In Friedel-Crafts alkylation reaction, benzene hydrogen is replaced by alkyl group. In Friedel-Crafts acylation reaction, one of the hydrogen is replaced by acyl group. Nitration reaction, nitric acid contains a hydroxy group, and hydroxy is protonated by concentrated sulfuric acid, forms OH2, which is a leaving group. So what you get is NO2, okay, nitrogen ion, and then benzene hydrogen is replaced by NO2. So the product is nitrobenzene. In sulfonation reaction, sulfur trioxide first is protonated by sulfuric acid, forms HSO3 positive, and then pi bond attack, and hydrogen is replaced. One of the hydrogen is replaced by HSO3. So the product, you have SO3H on the benzene, which is called sulfonic acid. Homework. Please work on problems 16.1, 16.3 to 60.7. Also work on some other additional problems in the textbook.